was a little bit of the Beatles. That was Here Comes the Sun. A little nice introduction on that. Okay, to get you in the mood for learning a little bit of trigonometry. So now we get into the part of calculus that deals with some trigonometry. To begin with, we're going to develop the idea of the derivatives of the 6 trig functions. And to start that and to learn that, you have to understand these 2 limits right here, because they're going to be utilized in the proof of the derivative of sine and cosine. So I'm going to start just real simple on a calculator with this first one here. So if you'll put this in the calculator with me here, we're going to put in sine x over x. I'll put that in y1. So I put in sine x, close parentheses, divided by x. You want to make sure that you're in radian mode. So I'm going to press my mode button. So I am in radian mode. And as far as a window, we're looking at the limit around 0. So what I'm going to do is kind of set up this window kind of similar to this graph. Maybe we'll go maybe up to, let's see, 10 maybe. We'll go negative 10 to 10. And this is in radian mode. And then I'm going to maybe scale it by 2.5 like this graph is showing. And then we'll go negative 1 to 1 on the y-axis, negative 1 to 1. And scale that by 0.2 the same way that this graph that I gave you is. So I'm going to graph this out. It's an interesting looking graph. There is a bubble here because we are, if h is 0, we're undefined. So we do have that bubble right there. So one of the first things we learned how to do was use the calculator to estimate limits. So let's trace at a number that's real close to 0 from the left-hand side. So I'm going to do negative 0.001 like that. And you can see that's pretty close to 1. I'll do it one more time. 0.00. I'm only meant to put a couple of zeros in it. Okay, so anyway, you can see that we're getting close to 1. Okay, the right-hand limit, we'll do the same thing, but we'll trace a number just a little bit bigger than 0. Like we'll do positive 0.001. And you can see pretty clearly that's also approaching 1. You can tell by the graph. And then the two-sided limit would also approach 1 like that. So that would be how you could use a calculator to verify visually and just with some approximation techniques what that limit is. Another thing we learned a little early in the semester is the squeezing theorem. So this is an inequality that holds for values fairly close to h. I'm not going to go through where the inequality comes from really. But what we're going to do is use the squeezing theorem. So we're going to do the limit of the cosine of h as h goes to 0. So that would be the same as the cosine of 0. And remember, on a unit circle, at 0 radians, we have the 0.10. Cosine is the x value. Therefore, that's equal to 1. Okay, then we'll do the limit of the inequality on the right. So we'll do the limit h goes to 0 of 1 over cosine h. That will be 1 over cosine 0. So that's 1 over 1. So that's equal to 1. And then by the squeezing theorem, we can conclude, therefore, that the limit as h goes to 0 of sine of h is equal to, sine h over h is equal to 1 by the squeezing theorem. Okay, so that one we've done a nice proof of. That limit's going to pop up in our development of the derivative of the sine. Okay, I'm going to look at the second inequality. And this one I'm just going to do on the graphing calculator. I'm not going to do a squeezing theorem or any other formal proof. We're just going to look at this graph. So let's put in, and you have to put this in like this. We have the cosine of x minus 1. Close parentheses all over x, and we'll do a pretty similar window than what I had on the previous problem. You get a problem like that. Now you do have a bubble right there. So again, we're interested in this limit as x goes to 0. So if we do this left-hand limit, let's just do this numerically. Let's trace a number a little bit to the left of 0. So that would be, that's given a scientific notation answer. That's going to 0. You probably see it a little bit more clearly if I just did negative 0.01. So you can see that's getting close to 0. All right, and you can tell this visually. And then the same thing would happen with your right-hand limit. Trace a number just a little bit bigger than 1. That again is approaching 0. And then therefore the two-sided limit is also going to be approaching 0 like that. So we're just going to do that numerically. So we have these two limits now, and they're going to be useful when we're doing our derivatives then. Okay, the other thing I wanted to remind you of in this section is these are just some of the real important identities that you'll use from time to time. You want to know the real basic identities. The basic identities are the reciprocal identities, the Pythagorean identities, and the quotient identities, like that. And even odd will show up a little bit. Cofunctions, understanding what a cofunction is really important. We're going to use some difference identities in our derivation of the derivative of sine and cosine here in a minute. And then here's double angle identities like this. So the more of these things you know and memorize, the better off you are. I'm going to, on this page, before I go to the next page, I want to show you a couple of things that will help you maybe to understand these at a little bit deeper level. So for instance, on these Pythagorean identities, really what we know is we know in a unit circle that x squared plus y squared is equal to 1 squared. That's the Pythagorean theorem. And the cosine is x, so you got to remember that in a unit circle, the x value is the cosine of theta. The y value is the sine of theta. That's in a unit circle. So all of these things develop from that idea. So this would give you cosine squared theta plus sine squared theta is equal to 1. Okay, that's why we call it a Pythagorean identity. Now, what I want to show you is how these other two things come from. You can do pretty simple derivations. I do this all the time when I forget this. So let me write this identity like this then. So let's start with sine squared theta plus cosine squared theta is equal to 1. And what I'm going to do is divide each term by cosine squared theta. And what I'll get is, this is the tangent. Okay, we have the quotient identity that says the sine over cosine's tangent. So this part right here would be the tangent squared theta. This part here would be 1. That cancels out. And then 1 over cosine is the secant. So this would be equal to the secant squared. So that's where that second Pythagorean identity comes from. Okay, these things pop up so often, I think it's important to either just memorize them, or the way I do it, I just know the sine squared plus cosine squared equals 1, then I derive the other two all the time. And I do it in my head. Okay, so we got sine squared theta plus cosine squared theta. Now what I'm going to do is I'm going to divide everything by the sine squared theta. And if I divide everything by the sine squared theta, the other Pythagorean identity pops up. See, that's 1. The cosine over the sine is the cotangent squared theta. And then 1 over sine, if you look over here, 1 over sine is the cosecant squared theta. So you end up getting that third identity like that. Okay, so those are things that are worth knowing. The other thing is on these quotient identities. The way I look at this is the tangent of theta is y over x. That's the definition of a tangent. Well, in a unit circle, the y value is sine theta. The x value is cosine theta. So that's where that comes from. See, all this stuff can be derived from the unit circle. All these basic identities come from there. And the same thing happens with cotangent theta. Cotangent theta's definition is x over y, but in a unit circle, x is cosine, y is sine theta. So that's a quick overview of some of the identities. And I'm not going to go through all of them, but those are important enough to know that that you want to know how to derive those if you have to. Okay, so if you know the unit circle and the definitions of the 6 trig functions, you can figure a lot of these things out. Okay, so the next thing we're going to go to is we're going to do a derivation of the derivative of the sine and the cosine. And like any of these things, we have to pull out the definition. We know the definition of a derivative is the limit as h goes to 0, and then we have the difference quotient, f of x plus h minus f of x all over h. So the derivations are going to utilize that, and they're going to utilize a sum difference identity also. Okay, so the way this goes is like this. The derivative of the sine, when we put this in the difference quotient, would go like this. Okay, we'd have, and I always like to just kind of tell students, just put 2 brackets all over h. And the way this goes is like this. Okay, whatever we're taking the derivative of goes there. That's f of x, so that's sine of x. And then the f of x plus h will be the same thing, but the x changes into x plus h. So if we work with this difference quotient, we should ultimately be able to work out that this is equal to the cosine of theta. Okay, so here's how this goes then. We're going to work with an identity. So we have the limit h goes to 0. And then I'm going to use this sine sum identity right here. And I always remember it this way. It goes sine, cosine, sine, same sign. I think of that like a little, not a rap or something, you know, like sine, cosine, sine, same sign. Okay, it sticks in my mind for whatever reason. Okay, so this goes like this. We go sine, cosine, same sign, and then backwards. Cosine, sine, like that. And then I'm going to bring down that minus sine x, like that, all over h. So what I'm doing with this then is I'm utilizing that difference identity. Now what we need to do is we need to see how we can put this together. The way I look at this is, you know, some of these things have x's in it, some of these things have h's in it. So we're going to break this up in a certain way. Okay, so let me show you how we're going to put this together. What I'm going to do is I'm going to group together these things right here. I'm going to split this apart like this. So I have the limit h goes to 0, and then I'm going to write this as sine x cosine h minus sine x over h. And then the leftover part, I'm going to group it together in a different fraction. So I'm going to write that as cosine x sine h over h like that. Okay, now limit laws are a big deal. So we know that if we do the limit of a sum, we can break this down into the sum of the two limits. So I'm going to write this first limit as the limit h goes to 0. I'm going to factor out this sine x, just some basic algebra. So I'm going to have sine x times parentheses cosine h minus 1 all over h. Then I can do the limit of the second part. So I'm going to write this as limit h goes to 0 cosine x sine h over h like this. Now what I want you to realize here is we proved two limits. We looked at this limit right here in the previous page, and we also looked at the limit sine h over h. Now what happens on this is there's a limit law that says constants come in front of limits. And see, we're doing a limit as h goes to 0, so the sine x can be treated as a constant because it has a different variable. Same thing with the cosine. So what we can do is take out the sine x, then we're going to do the limit h goes to 0 of what we already proved in the previous page, that, and then we're going to bring the cosine out of the limit. That's like a constant. We treat it as a constant. And then we have limit h goes to 0, and then we're left with sine h over h like that. Okay, so here's what happens. If you look at the previous page, we had these two limits. We had the limit of sine h over h was 1. The limit of cosine h minus h minus 1 over h was 0. So now we're ready to put this together then. Okay, so this thing right here was 0. This thing right here was 1. So what we get then as our conclusion is we get sine x times 0 plus cosine x times 1. Well, that will go to 0, so we have 0 plus cosine x. Therefore, that's equal to cosine x. Okay, so that is a proof that the derivative of the sine is the cosine. So you're going to have this derivative formula. That's where it comes from. All of these derivative formulas, are derived from the difference quotient primarily. Okay, so that's how that one goes. That's a nice proof. You do have to use a trig identity, and you have to use those two limits we proved on the first page of the notes handout. Okay, the next one I'm going to do the same way. We're going to start off with f prime of x. We're going to set up our limit as h goes to 0. Again, I like to write 2 brackets, and then all over h. And then again, whatever we're doing a derivative of goes in the second bracket, so it's cosine x. What goes in the first bracket is f of x plus h, so just change the x to x plus h. Okay, so we're going to have that, and then we're going to have to pull out this identity. So we have a cosine sum identity, and I always think of this like cosine, cosine, sine, sine, different sine. So I'm going to do this. Cosine x, cosine h, sine x, sine h, different sine. I don't know why that sticks in my head, but it does. Cosine, cosine, sine, sine, different sine. Okay, and I even tap on my desk to get a little rhythm going there. Okay, it's kind of like a rap or something. All right, so when we put this together, it goes like this. We have the limit, h goes to 0. Now we're going to go cosine, cosine, sine, sine, different sine. Hopefully I'll get that stuck in your head. So cosine x, cosine h, sine x, sine h, different sine, then bring the minus cosine x down all over h like that. Okay, now what we're going to try to do is work this out in a similar way. We're going to try to put this together in a certain way. So the way I'm going to put this together is like this. If I go through and put these things together here, get those put together, and then put this separate, let's see if we can get this to work. The reason I'm thinking this through is because sine h over h, I know the limit of sine h over h, so I want to get that in that problem. So let's put this together like this. We'll have the limit, h goes to 0, of cosine x, cosine h, minus cosine x, all over h. We're just splitting this fraction apart. Valid algebra, then we're going to have minus sine x, sine h, over h. I'm just splitting the fraction apart and using the same denominator. Okay, now in this one, we can factor the cosine out, and also we know the limit of a difference is the difference of the limit, so we are going to use a couple of limit laws. So let's write this as limit h goes to 0, cosine x gets factored out, so we have cosine h minus 1 over h, then minus the limit, h goes to 0, of sine x, sine h over h. Okay, so like the last problem, see these limits pop up in here. The cosine h minus 1 over h, we figured that limit out on the first page. We also figured out the limit of sine h over h. So it works like this. This is a constant. We're doing a limit as h goes to 0. So since this is a different variable, that can be treated as a constant, and constants can be brought in front of a limit based on limit laws that we learned. So we're going to get cosine of x multiplied by the limit, h goes to 0, of cosine h minus 1 over h, minus, take the sine x out, times the limit, h goes to 0, of sine h over h. Okay, now we're ready to put this together. Remember, this thing right here was 0, and this thing right here was 1. Okay, so we end up getting the cosine of x multiplied by 0 minus the sine x multiplied by 1. Okay, that cancels out, so you are left with 0 minus sine x. So you are left with negative sine x. Okay, so what we get then is this second derivative rule. The derivative of a cosine is negative sine x. Okay, so once we get the derivative of sine and cosine, we can use trig identities to figure out the identities of the other 4 trig functions. Okay, so that's how that goes. The next thing that's worth looking at is the graphs of the functions and their derivative. I think this is a nice diagram to just look at and think about a little bit. So this is the sine. This is its derivative. Okay, we have the derivative of the sine is equal to the cosine x. And from trig, hopefully you remember how your graphs go on the sine and cosine. So the idea, this graph in black is the sine of x. It has a point 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and then 0. That comes from the unit circle. So remember when we learned to graph derivatives, we always said, okay, where is the derivative 0? Well, the derivative of the sine is 0 on this interval in 2 places. So that means that if you graph the derivative, the y value will be 0. Okay, so that becomes an x-intercept on the graph of the derivative. Same thing here. So see, this gives a point. We have a tangent line that's horizontal. So we get on the graph of derivative, the derivative value is the y value. That's equal to 0. And then we kind of learned about this. The derivative is positive. Or I'm sorry, the function, the sine is positive, has a positive sloping tangent line. Therefore, the graph is above the x-axis. Then you have a negative sloping tangent line, so you're below. This point right here is kind of where the slope maxes out, and then the slope starts getting smaller. So we still have this negative slope. So we have this entire graph of the derivative below the x-axis. And finally, the slope of the tangent line on the sine's positive, so we're back above the x-axis like that. So that's how that works out. If you graph the derivative, the graph of the derivative of the sine x turns out to be the graph of the cosine x. And it works the same way here. What we learned is the derivative of the cosine x is negative sine x. Okay? So if you take the sine x graph, which is in black here, and reflect it, it becomes this. Okay, so basically the black graph here, when you reflect it, becomes this pink graph right here. So again, it's the same thing. Slope of the tangent line 0, therefore x-intercept on the derivative. Okay, slope of the tangent line 0, x-intercept for the graph of the derivative. Another place where it's 0, so you got that. And then you have a negative derivative, meaning you're below the x-axis. Still have a negative derivative, but it's getting bigger. It gets to 0. So see, you got this area below. The slope gets its maximum right there, and so forth. Okay, so that's a good thing to analyze and make sense of the graphing of derivatives that we learned. Okay, so that'll give us a good start on that. Okay, so now what we're going to do is we're going to focus on doing some derivatives that only deal with a sine and a cosine. So we learned 2 rules. I'm going to write these 2 rules up here. The derivative of the sine is the cosine. And that's easy to remember. The sine and cosine are co-functions. So sine, cosine. All right, you're going to find that derivatives have something to do with a cofunction. We also proved that the derivative of the cosine is negative sine x. So again, those are cofunctions, sine and cosine. Okay, so when we do the derivative, we can do some of these in our head. So if we do dy over dx on this one, we're just doing the derivative of the sine x plus the derivative of the cosine x. Now, you don't have to write that step. I'm just emphasizing that the derivative of a sum is the sum of the derivatives. So now what we would get is the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. So this derivative would be cosine x minus sine x. Okay. And again, that one is one that you could easily do in your head. I like when I introduce ideas of derivatives to kind of be fairly technical about utilizing derivative rules. Okay, the next one now, you have two functions that are being multiplied. So you have to work with the product rule. So what I'm going to do on this is, just as a reminder, I'm going to put the product rule over here. So if you are doing the derivative of a product, a first times a second, it goes like this. It's just the first times the derivative of the second plus the second times the derivative of first. So you have to use the product rule in order to get this derivative then. Okay, so let's put this in the product rule. So I'm going to have f prime of x. And again, what I do is I write down the first, which is sine x. I multiply by the derivative of the second. Then I add to that. I do it backwards. I write down the second. And then I multiply by the derivative of the first. So that is just doing exactly what that product rule taught us. First, derivative of second. Second, derivative of first. Okay, so these two derivatives right here, we know. So we can go ahead and do that now. So what we get is the sine of x. The derivative of the cosine is negative sine x. Okay, move to the next part, bring down the cosine. The derivative of the sine is a cosine x. So what we get is we get negative sine squared x plus cosine squared x like that. Okay, now this is an identity. Okay, and again, I'm going to go back to the first page here. If I write this backwards, what's going to happen when you're dealing with trig functions, if you can use an identity, you want to use it. Okay, so let me go back and show you what cosine squared minus sine squared x is. So if I go back right here, the cosine squared x minus sine squared x is the cosine of 2x. So in this problem, you could go through and simplify this, and you would want to do this, take it all the way to the cosine of 2x. Okay, if you can use an identity, use an identity. And there's more than one way to do that. That's, to me, is the simplest way to do that. If I know that identity and have it memorized, then I can figure this out pretty easily. What I recommend that you do, if you're doing derivatives of trig functions and you don't have all your identities memorized, then probably print out kind of a cheat sheet of identities and keep in mind that this will pop up when you're doing these problems. Okay, so that takes us through the first two. Now this one, we haven't learned what's called the chain rule yet, so I'm just going to write this as sine x times sine x. And again, what I'm going to do is I'm going to have to use the product rule on this. Okay, so when I get my derivative y prime, again, I do the first, I multiply by the derivative of the second, plus the second, multiplied by the derivative of the first. Okay, can't go wrong on that one. Okay, so we got first, derivative of second, second, derivative of first. Okay, and we know these two derivatives. Okay, we proved the basic rules for the derivative of sine and cosine. So we have sine x here. The derivative of a sine is a cosine x. And we get the same thing over here. We get sine x times cosine x. Well, see, these are like terms. So you have two of these. So we have 2 sine x, cosine x. But don't stop here. Look at identities. So 2 sine x, cosine x. If you know your identities, will ring a bell. Let me go back to that page, that first page, and show you where this is. Okay, so look right here. 2 sine x, cosine x is sine 2x. Okay, so we can go ahead and take this one step further and just write this as the sine of 2x as our derivative. Okay, so again, be on the lookout for those things when they pop up. Okay, all right, so those are some basic derivatives, and you have to use identities a little bit within those then. Okay, let's go to the next one, example 6. This is a quotient rule. You have two fractions, so you have a quotient rule. And the quotient rule goes like this. If you're doing the derivative of a fraction, I like to just say top bottom, then it goes like this. It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so we're going to utilize this when we do that. So basically we're going to have the top is going to be the sine x minus 1. The bottom is going to be the cosine. Okay, so when we do the derivative, y prime, or you could say dy over dx, put it in the quotient rule. So do the bottom, multiply by the derivative of the top. I'm just going to set it up in the quotient rule right now. Minus the top times the derivative of the bottom. And that would be all over the bottom squared, which we just write as cosine squared x like that. Okay, so we got that in the quotient rule. I'm just going to kind of write that on there. We did the bottom. We're doing derivative of top, top, derivative of bottom, bottom squared. Okay, just to emphasize how that went. Okay, so now what we got to do is we have a couple of derivatives that we should be able to do. Okay, so we need to work those two things out. Okay, cosine x comes down. Okay, now when we do this, the derivative of a sine is a cosine x. The derivative of a constant is 0. So you could think of that part right there, that derivative is 0, so you don't really have to write that in there. Okay, move to the next part, bring down the sine x minus 1. The derivative of a cosine is negative sine x. And then this is all over cosine squared x, like that. Okay, now we need to multiply this out, see if we can simplify, and then again we'll kind of look and see if any identities pop up in this problem. Okay, so what we get here is cosine times cosine is cosine squared x. You got to be careful about how you distribute this. See right here, you have a negative sine times a negative sine, so that's a positive cosine squared x. And you got to be careful here right there. So you have a negative times negative 1 is a positive sine x, but then that negative distributes through. I think a lot of students would do better on that part of the problem if they just did this. If maybe you wrote this as minus sine x times sine x minus 1. Just press that button. Okay, like that. That would be positive sine x times sine x minus 1. So then when you distribute, you get sine squared x minus sine x. So whatever works for you. I think sometimes students struggle a little bit with these signs here on that part of the quotient rule, so be careful about that. Okay, now that's all over cosine squared x. Okay, so we've done our derivative. The derivative is finished. We need to look at identities. Okay, so here's what happens on this. I see an identity right here. That's a Pythagorean identity popping up right here. So what you learned is the identity sine squared x plus cosine squared x equals 1. So I'm going to replace that whole thing with 1. So now I have 1 minus sine x all over cosine squared x. Okay, but there's more you can do. Okay, if you take this identity right here, if you solve this for cosine squared x, you can rearrange this. You get cosine squared x equals 1 minus sine squared x. Okay, so what I'm going to do is I'm going to replace the cosine squared x with what it's equal to in that identity. So I'm going to write down that I have 1 minus sine x over 1 minus sine squared x. Okay, there's still more though, because you can factor that denominator. That denominator is a difference of two squares. So you get 1 minus sine x all over, and then when you draw your two parentheses to factor, you have 1 and 1 to get the 1, and then sine x times sine x to get the sine squared x, and then plus minus like that. So what you have then, see, is these things will cancel out, and when they cancel out, you have a 1 in the numerator. So the answer to this problem, that derivative after all that work, would be 1 over 1 plus sine x, and there isn't any identities that will take that any further for us. Okay, so this is what's going to happen on these problems. There's going to be times when you don't have to use any identities, but there's also going to be times when you do. Okay, so that's how that one works out. Okay, I'm going to do example 7. And anytime you need to pause the video and, think through what I did so that you follow it, then you can do that. That's the benefit of watching videos. Okay, so example 7. So I'm going to move this over here, kind of zoom in on this. And again, this is a quotient rule. Okay, so we're going to throw this one in the quotient rule. So the derivative y prime, we're going to have the bottom multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom all over the bottom squared. That didn't really leave a lot of room on this handout to get all these things done real well, I don't think. Okay, so let's go ahead and work this out then. So we need to do this derivative, and we need to do this derivative, which we can do in our head. So what we're going to have is 1 plus sine x. The derivative here is going to be negative cosine x. Okay, the derivative of sine is cosine. The derivative of 1 is 0. So we have that. Then we have minus 1 minus sine x. And then the derivative here is 0 plus cosine x. So that's just going to be times the cosine x. Then all over 1 plus sine x to the second. And we need to see what kinds of simplification we can do in here then. Okay, so let's see. On this one, let's go ahead and we could either factor the cosine out. You could factor a cosine out if you wanted to. Or you could distribute. I think I'll just distribute on these things right here. So I'm going to do that. When I do that, I get, it looks like I get negative cosine x minus sine x cosine x. Okay, then I'm going to do this distributive property. So that's negative cosine x. Okay, then I've got this negative negative, so that will be plus sine x cosine x all over 1 plus sine x squared. Now you want to leave that denominator alone because you always want that denominator to be in a factored form. So it looks like what happens in this problem is we end up getting this. These cancel out. Let's see. So these things will cancel out. And then we'll have left over these like terms. And this will be a good answer. I mean, this will be negative 2 cosine x over 1 plus sine x to the second. Okay, you could, about really all you could do on that is multiply that bottom out. You might end up being able to use an identity for sine squared x. I just don't think that would take us much further. So I'm just going to leave that one alone right there as the answer to the derivative. Okay, so that gives us a pretty good group of derivatives with sines and cosines. So what I'm going to do is, if you need to pause the video, pause it now. I'm going to go ahead and move to have you do these two problems and then the problems on the next page. So there's 4 problems I'm going to have you look at, and that will wrap up this part of the video. So I'm going to pause the video. As soon as you've worked these out, resume and check your answers, if you will. Okay, so here is the answers to 1 and 2. Number 1, you didn't really have to use any identities on. This was a product rule. And a couple of key things on here. So I'm doing the first times derivative of second plus second times derivative of first. So that's set up in the product rule. Then when I bring the x squared down, the derivative of sine is cosine. bring the sign down, the derivative of x squared is 2x. And really there isn't anything else you can do with this. You could, I usually like to write things in front of the sign. So I write it this way. You could factor an x out, but you don't have to. So either of those answers is acceptable. Okay. Number 2, there was an identity that popped up in this towards the end. Excuse me. Okay, so this is another product rule. So I write the cosine squared as cosine times cosine. Then it's first times derivative of second plus second times derivative of first. Cosine comes down, derivative of cosine is negative sine x. Same thing happens here. Now, I like to write sine x, cosine x, because there's an identity. So I put these things backwards. I wrote it as negative sine x minus sine x cosine x. Those are like terms, so you get this. Now, there's an identity that says the sine of 2x is equal to 2 sine x cosine x. So I just kind of put that negative to the side, and then this part right here, 2 sine x cosine x, is sine 2x. So you would want to go all the way down to that point right there using that identity. Okay, look for identities. Like I said, when you're working these derivatives out, identities are likely to pop up from time to time. Okay, so that's how 1 and 2 go. All right, I'm going to move to the next page, and this will wrap up the video here. Okay, so number 3, I got cosine x over sine x plus 1 to the second. You really can't take that any further. Don't need to. You could FOIL out the bottom. Just really wouldn't make anything any simpler. So I think that's just good to leave alone. Okay, these problems on this page are using quotient rule. So I do the bottom times derivative of top minus top times derivative of bottom over the bottom squared. Okay, so I bring the sine x plus 1 down. Derivative of sine x is cosine x. Bring the minus sine x down. And then the derivative of this part right here is cosine x plus 0. So that's cosine x. Now what I did is I multiplied out. So I have sine x cosine x plus cosine x minus sine x cosine x. You do have cancellation of terms, so you're left with cosine x over sine x plus 1. And again, there really isn't anything else you'd want to do with that. Number 4 is interesting because it did have an identity in it, and it simplified quite a bit. So if you made it all the way down to 1 over sine x minus 1, you did good. So this is a quotient rule. So again, it's bottom times derivative of top minus top times derivative of bottom over bottom squared. Okay, derivative of cosine is negative sine. Derivative of sine x minus 1 is cosine. So you got this, and then what I did is distributed, so that's negative sine squared x plus sine x minus cosine squared x. Now, whenever sine squared shows up, you think immediately about this identity right here. The sine squared x plus cosine squared x equals 1. So I put these together and I factor a negative out. So I didn't really show this step over here. But what I'm doing is I'm really doing sine x minus sine squared x minus cosine squared x. I'm just rearranging it. Then I can factor this negative out of this like this. You got to convince yourself that that's the same thing. And then once you do that, this gets replaced with 1. So we know sine squared plus cosine squared x is 1. So now we get sine x minus 1. And then you can cancel one of those factors out. Okay, like that. I put the sine x minus 1 on purpose so it would match up with this. Okay, so that goes like that. You have the cancellation of term and you end up with 1 over sine x. Okay, so that should wrap us up on that section then. And the second part of the video, we'll look at the trig functions, the rest of them. Okay, so I hope you enjoyed the video. Take care.